Yeah. Good afternoon to one and all, and hearty welcome to you, ma'am, to NGRI. And today we assembled here to celebrate the International Women's Day, which is celebrated globally on March 8th every year. And as we know, the purpose of the day is to uphold women's achievements and recognitions and focus attention on women rights and gender equality. So, okay, let us celebrate in our own way. Like India has rich values and culture, which says "Yatra naryestu pujyante tatra ramante devta." So, we the ladies are in that level and hope and wish the whole world should keep us. I emphasize should keep us in that stature for its own benefit. With this brief intro, it is my pleasure, ma'am, to invite you onto the dais along with our director Virendra Mani Tiwari, sir. Please, ma'am. Yeah, beautiful flowers from our own garden to the beautiful lady on the dais and to our respected director as well. I request Ms. Josna to present a bouquet to Professor Sanghamitra, ma'am. I request Ms. Shikha to present a bouquet to our director, respected director. Now I would like to request our director to introduce today's chief guest.
Our, our honorable chief guest today for the International Women's Day celebration, Professor Sanghamitra Bandyopadhyay. Dear colleagues from CSIR and GRI present physically in this hall, online media, former directors of the CSIR, NGRI, Research Council members, and other distinguished colleagues who have joined through online. It's a great pleasure of welcoming all of you while we celebrate the International Women's Day. Though we celebrate it every day, but today we are marking it in terms of acknowledging the contributions of our fellow colleagues in their respective areas. We all have been witnessing in the present era that how significantly the women researchers and engineers have contributed in the India's several missions, and one of the very big achievers in the science and engineering is with us today. You know that Professor Sanghamitra Bandyopadhyay does not need any introduction to this audience particularly, and to the audience, those who have joined online. Nevertheless, it is pleasure always to let the younger colleague know that we have with us a distinguished colleague to inspire and tell us how can we make our work useful for the betterment of the society, for the betterment of the country. I happen to know Sanghamitra decades back, incidentally, when we received in same year INSA Young Scientist Award 2000. The journey of Professor Sanghamitra must have been very, very tough and very, very hard. Nevertheless, her achievements are even bigger than what anybody can think of. She has been with the Indian Institute, Statistical Institute as a director for quite some time. But what makes her very different is how the engineering sciences can be used, their applications in the biological sciences. We talk of the interdisciplinary research. Here there is a person who cut across different discipline and shows that science and engineering are not two subjects, not two areas, but rather it's same area. It's that, and the ladder is nothing but the excellence, and excellence, which as per the CNR Rao is a ladder which is endless. Professor Sanghamitra is a recipient of the highest science prize in the country, Kanti Swarup Bhatnagar Prize. One of the another very high considered flight, Infosys Prize, the International Prize, TOAS Prize, and several other awards to mention. And she is fellow of all academies of India, the World Academy of Sciences, and most importantly, she is one of our well-wisher, one of our guide, being a part of the CSIR Society, a member of the highest apex body of the CSIR chaired by Honorable Prime Minister. She is also member of the PM stack, and she is known for her path-breaking work for utilizing the machine learning for the applications in the biological sciences, often known as computation. To think about her academic achievement, but what makes her difference from other, that how she could able to achieve all while parallelly doing and taking care of the family. And that's how makes her a role model for all of us in society. And we have taken this opportunity while we wanted to celebrate the International Women's Day at CSIR NGRI to invite her. And we are so grateful, madam, that you have kindly agreed to personally come and grace this occasion and interact with the fellow colleagues of CSIR NGRI, particularly the young women researchers and the scientists. I'm sure with your gracious presence in our institute, we will certainly take a message forward that the driver of the science remains the excellence, nothing else. And it crosses the boundary. It does not have boundary of gender. It does not have boundary of the region, religion, and so on. And this is what the theme of the International Women's Year, this inequality, to eradicate inequality in society for the prosperity in the future, for the sustainability in the future. And through her scientific work and through her personal experiences, she is here with us to inspire and take the message forward of doing science, harnessing the benefit of science and engineering for the benefit of humanity. So thank you once again, Maiban, and welcome to you and all colleagues who have joined online and physically on International Women's Day. And I greet all our colleagues who have made us proud this year by either achieving rewards or awards or performing uh, very high during the last year. And greetings to everyone, though belated, of International Women's Day. We hope, and I always quote, I don't wish to forget the line which has been put by the youngest Nobel laureate, Yousafzai Malala, says that our society can't progress if half of us are held back. And that should be our motto, that should be our uh, objective, to see that our society progresses, our society brings the equality in all terms. So thank you very much once again, madam, and welcome to everyone for the session today, Gender Equality Today for Sustainable Tomorrow. Thank you, Vasanti, for making all the arrangement and all other colleagues. Let's move forward.
Yeah, thank you so much, sir. Now it will be our pleasure to listen to Professor Sanghamitra, ma'am. Please, ma'am, deliver your International Women's Day lecture.
Shall I just speak onto this in this mic and okay, and the slides? And we have the slides somewhere. Doesn't show. I mean the slides. Yeah, I give it in the. It is already there. Yeah, you are. If it has gone, that's it. It's because from the Apple to so some.
A little bit near to you so that.
Okay, otherwise I'll take that mic.
Yeah, you can do.
I can stand also. नीचे भी होगा?
Yeah.
It's okay. Okay. So thank you very much, Professor Tiwari, for the nice introduction. Indeed, we were together in 2000 when we received the INSA Young Scientist Medal from whom? Virendra? इसने दिया कि Govardhan Mehta the, correct. And also a very happy Women's Day to all of you. Unfortunately, I could not come yesterday because we had several programs, including program of our own institute. But I mean, he asked whether it could be the next day, and next day I had some time, so here I am. I will try to, Professor Tiwari actually made my life simpler by just writing the title. So after you've given enough lectures, once the title is given to you, you can fit your talk to that. So I tried doing exactly that. But I made the presentation on Apple, and from Apple it has been transferred here. So that is why the benefit has gone to that side. So please, it's on the right side. Correct. That is how it should be. And I don't know what is going to happen in the next slides also. So I've not seen what is the situation of the slides. But a journey to harness artificial intelligence for human benefit. And I thought that that journey could be the journey of artificial intelligence, and also it could be my journey of into this world of artificial intelligence, where I've been working more in, as already mentioned, in computational biology, which has a very direct link to human benefits. So let me move on from there. My name is very difficult actually. The first name is difficult, last name is still more difficult. I have been at the, I will tell you a little bit about my institute also in the next few slides, but let me start paying my tribute to some of the women scientists of the 1900s in India. It's of course not an exhaustive list, but all of them faced a lot of trouble. A lot of trouble to do what they like to do, what their passion, where their passion lay. All of them faced huge trouble, and it is because of the trouble that they faced, the roads that they created, that we've been walking on those paths. And still, we know that the women have a lot to lot to achieve yet, many miles to go. So the path that we make through our struggles will probably make life easier for the generations to follow. These are some recent contemporary but senior women scientists, many of you whom you might already know. These are less senior. They are also senior, but less senior. This. Sure. Yeah. And this is a mathematician from my institute, Indian Statistical Institute, very young colleague. Got almost all awards. She's the youngest mathematics Bhatnagar awardee of the country. So it's not about woman or anything. It's overall youngest woman, youngest mathematician to get the Bhatnagar award. And yesterday she also got the Nari Shakti Puraskar from the president of the country. So women in science, what is the scenario? We can see that there are quite a few women, about 40%, who are earning their PhDs in STEM, in areas of STEM. In Europe, in France, and it's almost similar. As we come to Asia, the numbers are less, which is expected, I think. Percentages go down when we move into senior positions, and still less when we get into decision-making positions. And in general, we all know that women are older than men in comparable positions, or to get comparable salaries, women take longer. If we look at the Bhatnagar Awards, only 19 women till about 2021. 19 women and 584 men have won the Bhatnagar Awards. Even Madame Curie was not elected to the French Academy of Sciences in 1911 after having received Nobel Prize. So from those times, at least from this 1911 times, we've moved quite a bit forward. And in India, I must say that this bias was from the beginning little less. So right from, for example, right from our independence, women had the right to vote. In many places, they had to fight for that right. Here it came, and during the British time, that was difficult, but after independence, that was but natural. Now it's also women have a right to the property, and so a lot of changes have happened. But a lot of changes yet to happen. And in particular in engineering and mathematics, women are grossly underrepresented. I must say in mathematics in particular, it's not just about women. I think many students, they fear mathematics for some reason. I think it's because one, for finding mathematics to be easy, you would have to visualize mathematics. You would have to build a story around the math that you are doing, which many people may not be able to do, and therefore they find it very dangerous, this mathematics. So both men and women, boys and girls, they tend to go lesser into mathematics. And in terms of gender in mathematics, there's not a remarkable difference between men and women. We'll see. For the Nobel Prizes, this is data as of 2018, 51 women and 853 men have won Nobel Prizes. And you can see the distribution of the Nobel Prizes. Most of them have got, women have got the Nobel Peace Prize or the prize in literature. Then comes medicine, chemistry, physics, economics. Only one right now, two, because last year Esther Duflo also won. This is showing where the women are. What is the percentage of women in the workforce? From 1970s, there was a remarkable increase in the 1990s, but thereafter you see it's not gone up quite a bit. This is surprising, but that is how it stays around 25% in general. That's women work in the workforce in STEM. And where are they? Actually, if you look at these areas, you see in mathematics, the gender difference is not that high. This is, I forget where the source is. It is written somewhere in my notes. But you can see in engineering, the difference is very high. Very few women get into engineering. So in computer also, that's quite surprising actually. Why in computer and allied fields there should be less women, while in mathematics there are, it's almost an equal distribution, but possibly because many more men get into these areas. These are only percentages which are showing. And in India, you see, this is a 2020 report which says India tops the world in producing female graduates in STEM, but ranks 19th in employing them. So about 43% are graduating in STEM, but only 14% they are employed in R&D industry or R&D institutions. In the corporate sector, if you look at the gender gap, this is World Economic Forum report. As you can see here, the percentage of women in the board of directors, it's very high. It's very good in France, 43.4%. It comes down, UK is somewhere here, US is 21%, India is about 13.8%, with you see all the Asian countries here, India, China, Japan, Korea. So this less number of women, less percentage of women is an Asian phenomena, looks like. So what about women and science first? We'll come to what about women in science, but women and science, you see generally gender was not considered a variable in many of the experiments. So even in medical experiments, it was conducted on average size males. The fact that women show different symptoms, react differently to drugs was never studied. And interestingly, even rats and other animals were primarily male. This has been, so what was the result? That diseases were misdiagnosed, symptoms were misread to women, medicine dosage was wrong, and women's health was severely damaged. But this has been identified, people are aware now, and therefore gender is very often a factor in most of the experiments done these days. So gender is now a variable in many experiments. Now the question comes, why should we have women in science? Is it just that it sounds right, it's morally correct that we should have women in science, or is there more to it? Actually, when this is studied in deep, it is found that there is more to it. You can see here, there's a 2014 report which says that there were about half a dozen studies done by the likes of Goldman Sachs and Columbia University, which have found that companies employing women in large numbers outperform their competitors on every measure of profitability. A more recent Harvard Business School review, which looked into the venture capital industry, which is heavily male-dominated industry, it found that VC firms that increased proportion of female partner hires by 10% had a 1.5% spike in the overall fund returns per year and 9.7% more profitable exits. So many of these are only two sample studies, but there are many studies which indicate that having more women in the workforce with diversity of ideas, diversity of solutions, which the diversity of the perspectives that they bring to the table, profitability increases of companies. So that makes pure economic sense to have more women in the workforce. It's not just about sounding correct, being morally correct, ethically correct, or anything. It makes pure economic sense to have more women in the workforce, because it is my belief that anything that is morally correct and you do that only for a short period of time. Unless something makes economic sense, that is not going to sustain. So what emerges out of all these studies is having more women in the workforce giving more opportunities to the women actually is beneficial for not only the women, but for every one of us. All the entire community, the entire country, the entire world, science, whatever you can think of will gain the more and more women come into the workforce. So, in academic leadership position in 2015, December, there was this report in Economic Times that not a single IIT or IIM has a woman director. So there were some All India Institute of Medical Sciences, 31 NITs, of which, as you can see here, only one at that time had a woman director. By 2020, this has actually changed. So you can see now President INSA is a woman. There are several IIM directors who are women, who have been women. DBT secretary who's just retired was a woman. DBT has had women secretaries earlier also. Vice Chancellor of Calcutta University is a woman, of Jamia Millia, and so on and so forth. In 90 years of its history, Indian Statistical Institute in 2015 actually got a woman director. In 2020, gave a second term to the woman director. So things have changed. Things have changed and are changing. Of course, the pace has to be faster. I mean, we need more change. Now, seeing that women are less in engineering, they women or generally students do not like mathematics. Women are less in computer science. And also in physics. I have earned degrees in physics, in computer science and engineering. I did a PhD in computer science, became a lecturer in Indian Statistical Institute, moved on to professor and then on to director. And in spite of doing all that, I still have a family. So that is surprising. What happened? Why? What did it take? That is what I asked myself. What did it take? It didn't take too much, actually. It took enough sincerity, of course, commitment, to some extent, a non-compromising attitude. Not on every aspect, though, because every person has to compromise. So you choose your battles, which battle you would like to fight and which battle you don't want to fight. Because if you keep on fighting every battle, then energy will be lost. Yeah. So you have to choose your battles, which battle where you will not compromise and where you will compromise. So those are the battles one chooses for oneself. And I had an acceptance that a price has to be paid. So as Professor Virendra said, that in spite of all doing so many things in the external world, I still looked after my family. That is what I did not do. I really was not able to look after my family. I had 24 hours just like any other person. If I spend 10 hours in the laboratory, I can hardly have time for the family. But the good thing was my family accepted it. My family did not expect that I would, of course, there were certain levels of expectation, but nothing which bothered me too much. Nothing which I could not fight against sometimes. And sometimes I agreed, of course. So, but the acceptance that I have not been able to look after my family as many other women have been able to, that acceptance and that acceptance without the feeling of guilt is something which I had. So that was probably in my nature. And when my when my parents, my mother is no more, but mother, of course, in many of not only women, in men's lives also, mothers play a very important role very often. I don't think that is going to remain true in the future, because now mothers will also become very busy. So what role can a mother play in a child's development if the mother is not there at the home anyway? So I think that is going to change. But that is a change which one has to accept. Society will be unstable. We understand. There will be instability in the society. But then again, you might have heard about this something called game theory. Game theory, there's something called Nash equilibrium. So again, in that instability, some stable state will emerge. That is what we hope. That market forces will come into play. There will be a lot of instability, but from one stable state to another stable state, in between, we are going through this phase of instability. That is here, and that also we have to accept. So when my parents would sometimes say that, like a woman, I should be doing that, and would get upset when I don't do that, then my response often had been very guiltless, I must say, that when I get a prize, if you are so happy about it, then you must accept that I'm different from others. So if in good I'm different, in bad I will also be different. So don't expect me to be good everywhere. No, I cannot be. So, but these things actually are, I see in young girls, colleagues these days, it's there quite a bit. So that spirit is there. And I'm sure things are going to become very good. So women in science, as I said, it did not take me too much more than what it takes a man to reach whatever I was able to do. And primarily because I think I was fortunate. I had extremely supportive parents, at least who never said that you cannot do that. My mother often expected that, okay, you will do this and you will do that when you are small, you will help in the family. But never for once I was told that being a girl, you will not be allowed to do that. So I climbed trees, I rode motorcycles, I mean, um, I drove cars and everything that anybody is allowed to do, I was also allowed to do. And as I said, of course, a family which stuck to me. Rather than me sticking to the family stuck to me, didn't go away. That was a good thing because those, I mean, internal pressures are something very often it's very difficult to overcome. External pressures, externally you can fight. Internally, the fight becomes very difficult. And a son who accepted my absences. So what I feel is essentially often, as we all know, it's a mindset, and mindset changes can only happen from the very young age. We very often see in the kids' books that when a doctor's picture is there, it's a man. When a nurse's picture is there, it's a woman. When it's a picture of a kitchen, a woman is cooking. When it's a picture of a car, a man is driving. So these, from the young, in the young minds, they create those stereotypes. If we can do something about those books, change those books so that it becomes gender equal in some sense, maybe these automatic stereotyping of roles will change in the future. Childbearing is, of course, cannot change unless something happens in those in that research. Childbearing still remains a woman's responsibility, but child rearing need not remain only a woman's domain. That is very important. So these things are changing. These changes are now visible in the society. So now let me present you the Indian Statistical Institute into two slides. Established in 1931 on 17th December, so it's a pretty old institute, pre-independence, in a small laboratory in a college called Presidency College in central Kolkata by Prashanta Chandra Mahalanobis, who was a physicist by training. He taught physics in Presidency College, but a chance encounter with statistics actually made him realize that this particular discipline had great potential for human development and national development and human welfare. And therefore, with a group of like-minded people, he started the Indian Statistical Institute in Presidency College in 1931, which moved to its present campus. This is the present campus. It's in the northern fringes of the city about 2 decades later. Mahalanobis is very well known for the Mahalanobis distance, large-scale sample surveys, flood research. He spearheaded the second 5-year plan for the country, and the first computer in India came to Indian Statistical Institute in 1956. Mahalanobis had that vision. At that time, of course, the computer came for doing statistical calculations, very big statistical calculations, but there was, I think, a race between Bhabha and Mahalanobis, and Mahalanobis won that race at least, got the first computer in India to ISI. This is how we are placed. We are headquartered in Kolkata, and we have centers in Delhi, Bangalore, Chennai, and Tejpur. We have a center units in Hyderabad, right here, about a kilometer from here. And we have our colleague from ISI Hyderabad here. Thank you very much for coming. So Hyderabad, Mumbai and Pune, very, very small 2 units. And we have a branch in Jharkhand, a place called Giridih. These are the different scientific divisions that we have: applied statistics, biological sciences, computer and communication sciences, physics and earth sciences. In fact, we have a geological studies unit which could be of interest to you. In ISI, we have a geological studies unit and we have a fully mounted dinosaur fossil. I did not have time to put a picture of that, but it's very easy to see. It's called Isisaurus. It's a different species. It's named Isisaurus. And it's also called Barapasaurus tagori because when it was discovered, its femur bone, that the driver called Barapa, matlab big feet. So that's how Barapa came and Barapasaurus, and Tagore because it was mounted in the birth centenary year of Rabindranath Tagore. So, and we teach, our primary purpose, of course, we do a lot of research and we excellence, as Professor Virendra said, that indeed in ISI excellence is the mantra, and I'm sure here also that is what you all look for, excellence, and that's how science progresses anyway, through excellent work. So excellence has been, we put a lot of focus on peer review. Actually, we measure excellence more in terms of peer review rather than using the different parameters which are there, which we know. And we also teach our BStat, MStat programs, Bachelor of Statistics and Master of Statistics. These are flagship programs running for many years now. We have BMath and MMath. We have Master of Science programs in quantitative economics, etc. We have MTech program in computer science. MTech in computer science is the first MTech in computer science program in India. We also have very recently opened the cryptology and security MTech program, and quality, reliability and operations research. That program has been there also for many years now. We have postgraduate diploma programs, 1 year diploma. This program is very interesting, postgraduate diploma in business analytics. It's a 2-year program at the level of masters, but the unique thing about this is IIT Kharagpur, Indian Statistical Institute, and IIM Calcutta. The 3 institutes together, we run this program, 1 semester each. The students spend in 3 places, and the last semester they do industrial projects, and all the 3 institutes sign on the certificate that the students get. So this is really a unique and also a unique learning experience for the students. And of course, we have the PhD programs. So with that, let me come to a little bit of science that I do. As we all know, in fact, I think CSIR has a fourth PI or 4 PI institute also, right? Yeah. So the 4 paradigms of science: empirical, theoretical, simulation, and now we are here in the 4th paradigm era, which is data-driven science. So here the data is going to tell you, or from the data you would have to learn what is the science that created that data. So that actually requires a very strong collaboration between academia, industry, and government. And that is what I think is slightly weak in our system, and we must work together to address that problem. So artificial intelligence, because this data-driven science is also built around principles of artificial intelligence and machine learning. It has been around for decades. It's actually programmed, the intelligence that is programmed into machines, which is in contrast to the natural intelligence that we all demonstrate. So Turing test was devised in 1950 as a test to say whether a machine has become truly intelligent or not. And how is that? There is an interrogator who, on the other side of the wall, there's a computer and a human. The interrogator gives some written questions and gets some written answers, and that answer may come either from the computer or from the human being. And so the interrogator has to determine which player among the two is the human. So who is answering, whether the human has answered or the computer has answered. And it is said that the Turing test would have been passed if 30% of the time the machine is mistaken for a human. So while the machine has answered, the computer has answered, the interrogator thinks that it is the human who has answered. So if that happens at least 30% of the time, then we would say that the Turing test has been passed. Some amount of result came in 2014, but very recently there is a system which is now said that the Turing test has indeed been passed. So it's not easy. The Turing test sounds easy, but it is actually a difficult test to pass. So a machine has to be that intelligent to be able to mimic a human being. So what is artificial intelligence actually? These are programs with the ability to learn and reason like humans. That is fine. But we've also heard of machine learning. We are nowadays hearing quite a bit about deep learning. How are these things placed with respect to each other? So artificial intelligence is on the outside. A part of it is machine learning, where the machine actually learns something, learns to generalize to new situations. Okay. So these are algorithms with the ability to learn without being explicitly programmed. And deep learning is a subset of machine learning. For example, the artificial neural networks, which learn from vast amounts of data. And deep learning has a, you see, when you are doing till machine learning, from the real life situations, you would have to extract data, you would have to extract numbers and then feed it into your computer program. It could be a classification system, it could be a classifier system, whatever. Now suppose you have an image and you want to classify some regions of the image. Then also what you have to do, can you just open it for me once? So if you have an image, then you would have to extract some features from the image and then give it to the computer to do your classification. When you are doing deep learning, you do not have to extract those features. So you give the image as it is as input to the deep learning system. The system will recognize those features. So it will find some interesting features in that image based on which it will do its classification, because often a classification problem, I don't know whether you're aware of what a classification problem is. Classification problem is something like this, that you have, for example, you have some flowers, okay, maybe one particular flower, 3 categories of that flower, okay, and what you want to do is when you see a new flower, you want to be able to say automatically through the computer program which category this flower belongs to. Or a patient comes, you have learned whether how to distinguish between, let's say, a patient who has cancer and a patient who does not have cancer, a normal individual. So now a new person comes with some symptoms, and automatically through the computer program, you would like to classify whether this person has cancer or does not have cancer. So this is a 2-class problem. There can be multi-class problems also. So, so deep learning systems, essentially, they do not need the features. They will automatically extract the features. Now, very often we hear of machine learning, and when I have heard many people think that everything is artificial, and whatever is done on the computer is artificial intelligence or is machine learning. That is not true. So let us, through this example, just quickly understand what is machine learning and what is not machine learning. Suppose we have this database, okay, where we have the roll number of students, names, years, etc., etc. And we are giving a query, find all students who have taken the subject S1. So subject is S1, this student and this student has taken. Answer will be R1 and R2. Okay, so this is just retrieval. There is nothing machine learning here, no machine learning here. Okay, it's because the data is already there. It is just quickly retrieving the answer. That's all. But the answer is there, written there. So this is not machine learning. While if we show a system images of dogs and cats, so this is a dog, this is a dog, this is a dog. We label them. Okay, we tell the system that this is the image and this is the image of a dog, image of a dog, image of a dog, image of a cat, cat, cat. We tell the system will learn how to distinguish between a dog and a cat. And now we give this image. You see, this image, it has not seen before, right? It is not there in the training set. This is a new image. Yet the system will be able to tell you that this is a cat with high confidence. So this is machine learning, where the system is able to argue some information about an unknown situation. but it has learned how to distinguish from some known situations. So you need training data to train the system. But thereafter, it has learned some features of dogs and cats, which it applies to this image and is able to tell you with a high degree of confidence that this is the image of a cat. So this is machine learning. This is not machine learning. Now, AI, as we know these days, it's sort of becoming omnipresent. There are many, many domains which have applications, deep applications of AI. We know that in agriculture, in healthcare, smart cities, smart retail, etc., self-driving cars, applications of artificial intelligence galore. Okay, I will tell you about healthcare, but a little bit in detail, but agriculture. If you can monitor the soil conditions, the weather conditions, and give alerts to the farmers about crop diseases, or give recommendations about when to sow what, in what quantities, etc. So these are all areas where agriculture can benefit from applications of artificial intelligence. Let's say smart retail. When we are buying books or whatever on Amazon, very often we are recommended similar items that we might want to look at. And many a times those are not very irrelevant things. Those are reasonably relevant. Whether we buy it or not is a separate issue. But these are reasonably relevant recommendations. How does the system know to recommend these things? Because there are millions and millions of things to recommend from. Why does it recommend those particular things to me? It's because it has learned my characteristics. Okay, it has learned what people tend to buy together. So from looking at millions and millions of data, from millions and millions of transactions happening, it knows what people buy together. So from there, it recommends. Movie recommendation. All these are very great applications of artificial intelligence. So in the country, there's a lot of focus on AI in healthcare, agriculture, education, whatever. We've already looked at these things. Niti Aayog has brought out a discussion paper on this. And here, there are actually great opportunities in the domain of AI in India, because there are great opportunities for problem-driven basic research, innovative applications, and converting knowledge to wealth. India, and I must say in particular, Indian women cannot miss the fourth paradigm bus. And why Indian women? Because these things, artificial intelligence, machine learning, computer science, statistics, mathematics, they don't have anything masculine about them, right? Because masculine, wherever more strength is, physical strength is needed, that's where men will have an advantage, a natural advantage, physical strength. But these things do not require physical strength. It requires mental strength and mental abilities. And there, nature has not distinguished. So it is for us to actually look into these areas, as I said, in particular, because now with all the technology available, women are, I think, going to benefit hugely, in particular, because the more technology is coming in, the more dependence on physical strength is going down. So therefore, women will be at an advantage. Of course, again, that instability has to be there, because nobody gives up anything, any right, without a fight. So men will also not give up that general right, and nothing wrong with that, without a fight. But that fight has to be fought for the benefit of all. So we have, let's move on. So I don't want to spend time here, but the Indian scenario is not that good in terms of research. As you can see, the spending on research and development compared to US, China, Israel, Korea is very small in India. It's about 0.26 to 0.7% of the GDP. Even if you look at how many researchers per million population, again, India, the value is pretty less. In engineering publications, actually, we are doing reasonably well. We are ranked third in scientific and engineering publications with UC, but the percentage is much less, but then it goes down. China, as expected, has a very high percentage. And it also ranks 1 in the number of papers per dollar spent. So if this thing goes up, we hope that this will also go up. Okay, but we do spend much less on research. And also, compared to many other countries, the participation of the industry in funding research is pretty low in India. That also has to be addressed. So let's not focus on this. I don't think we have enough time for that. But let me come to some, just to give you some idea about the research that I do. So the revolutions that happened in healthcare have been several. One was of course, the discovery of the structure of DNA, which had it not happened today, we would not be doing what we are doing. I mean, we would not have progressed at all. This was crucial, discovery of the structure of DNA in 1953. Then came the revolution of genomics, where we started looking at entire genomes, meaning this entire set of genes in the organism, and moved on to systems biology. And now the revolution that is there is in convergence of different areas. No science now remains isolated. So life sciences is converging with engineering, with physical sciences, with mathematics, everything together. The COVID pandemic showed us how or what a great role mathematics, statistics has to play in even modeling the spread of the pandemic, etc. So convergence is what is happening these days. So as I said, the Human Genome Project was a 13-year-long project to understand what is there in the human genome. And what is that genome? You see, we know that we have cells. Body is made of, any organism is made up of cells. Each cell in a typical eukaryotic organism would have a nucleus. Inside the nucleus, there are chromosomes. And each chromosome is made up of if you look at the DNA strands, it's a double-stranded DNA. So, and it's like a helix that it appears. And this double-stranded, if you take out one strand, then it is essentially just a series of A, T, C's, and G's. And from every chromosome, if you take out one strand and place this entire thing one after the other, that's a very long strand of about 3 billion bases. Oh, sorry, 3 billion bases. 3 billion. These individual ATCGs are called bases. And there are 3 billion bases. What was the Human Genome Project? To look at what these individual positions contain. A, T, C. What is the sequence? A, T, T, A, C, G, 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 T, T, etc. So that was just what the Human Genome Project was. And there, actually, at that time, the technology which was available, you see, this is a long string, right? 3 billion bases long. The technology which was available could look at only much shorter strands, say 1,000 long strings it could look at and tell what is there, A, T, C, G, what is there. But the original strand is 3 billion bases long. So now it became a computational problem that I can cut that 3 billion long string into smaller pieces and then sequence the smaller pieces. That can be done. But how do I rejoin and rebuild the original string? So that is impossible, right? Now that this became a computational challenge. And how was it solved? It was solved by saying that, okay, do not sequence just a single strand of the entire genome. Make multiple copies of that. Cut each long strand around 1,000 small pieces of size 1,000. But you have multiple copies, okay? So once you do that, then if you think a little, you see maybe from one long strand you have this piece. From the other long you might have a longer string, but it is containing the top one. So once you start aligning these sequences, if you work it out, you will see now you have a way of keep on aligning and keep on joining. That now becomes possible. So this was, an interesting problem that the biologist gave to the computer scientists or to the mathematicians. It was solved mathematically, and had that solution not come, we would not know what the genome was. So these are areas where one discipline actually challenges another discipline and solutions come from the other discipline. So what I have been doing, I have worked quite a bit on something called the microRNA. And what is this microRNA? MicroRNA these are very small molecules. So this actually here, assume that this is a long that genome, okay, and long string of ATCGs. Certain portions are what are genes. Certain portions of this long string are the genes. And we have heard of genes. Every one of us, we have heard about genes. Certain portions are genes. From the genes, something called messenger RNAs are produced. Okay. And these messenger RNAs produce proteins. And these proteins are like active everywhere. Anything that we do, how we look like, this color of our skin, the color of the eyes, or whatever, hemoglobin. Hemoglobin is a protein. So all actions are through proteins. So proteins are important, but there is something called microRNA also, which gets created at some point of the time in the lifespan of the cell. And this microRNA actually interferes with different proteins. And one example of such an interference which can cause cancer is, you see, the cells are dividing, right? We know that cell division happens. And cell division happens, so new cells are created. At the same time, in order to keep the balance, cells have to be killed also. So cell killing is also natural. Cell death is natural. Cell birth is also natural. But cell killing, there are many different steps involved in that cell killing. There are certain proteins which are crucial for killing the cell. Okay. Now, if one such protein which was crucial for killing the cell becomes deactivated because some microRNA came and interfered with that particular protein, then what is going to happen? While cell birth happens, cell killing is not happening. And that we know, when there's an explosion of cells, that is cancer. So if we can identify which microRNA, and very often it is found that microRNAs are responsible for not only cancer but many other diseases. And that information is now available with us because of a lot of research which has happened. So if we are able to tell which microRNA may have caused this trouble, then we have some handle on the disease, we have some knowledge, and if we can inactivate that, deactivate that microRNA, then again the normal process will kick in and we hope to arrest that disease. So this is how usually diseases are understood. So what we did through machine learning is we tried to learn which microRNA will target which messenger RNA, because messenger RNA will produce the protein. And this was a target prediction problem. So we learned from several such pairs. So these are targets. We know that these are targets, non-targets, etc. So that we are able to argue or able to analyze an unknown pair and tell whether this particular microRNA will target this messenger RNA or not. So this is one target prediction problem which we solved, and which became actually, I mean, there's a lot to it, of course, which became very popular. This is our method, target miner, and we compared it with many other methods which were out there at that time and showed that this was doing very well. In fact, the results were so well accepted by the international community that there is a database called MIRBase of microRNAs, and our predictions were integrated in that database so that everybody could use this method. This is some time back. Building on that data, we analyzed in a graph theoretic way some cancer specific networks. So we have a breast cancer specific data from where we built this network of different molecules, and from there we found that at the topmost level of this network, some 5 molecules were coming up. And we observed that all these 5 molecules were microRNAs. This network actually has both microRNAs and genes, okay? And this is specific to breast cancer. So now once we understood that these microRNAs looked to be very important because they were controlling a large portion of this network, then we looked at information about literature information from the existing literature about the involvement of these microRNAs in breast cancer. And we found that 3 microRNAs of those 5 had literature support that they were actually involved with breast cancer, but 2 microRNAs, there was no literature information. So that became interesting. Is this a new information? Is this important? Is this good? So our work actually stopped there because we did not have the expertise to go on into doing the biological experiments. But much later, in fact, about 2 years later, one of these microRNAs was independently validated by another group, okay, who just looked, they did not collaborate with us, but they independently validated the microRNA and it got validated that it is important in cancer. So these, once we know these, then these become important markers actually. So once a new patient comes in, you can simply look at the microRNA values of that particular patient. And if this MIR 155, for example, has a high value, then you can make some draw some conclusions about the disease. So this was a similar results for colorectal cancer. We did, I'll not go into this clustering algorithm, but I'll tell you one last result that we have in drug design. So designing of drugs, of medicines. And here, these small molecules which act as drugs, essentially these molecules actually go and interact with proteins which are misbehaving. Let's say there's some protein whose normal function has become disrupted for some reason. And this protein is there inside the cell. It is getting created inside the cell. Proteins are 3-dimensional molecules, right? And they're not smooth molecules. They have clefts and cavities on their surface from where in one of these cavities, maybe some other molecule comes and binds. So this is called protein binding. Proteins bind with each other or with other molecules, and that's how they exhibit their functionality. Now, we have to identify that maybe this particular, these are called protein active sites. These are active sites where the action takes place. Some active site has some particular structure where a wrong binding is happening. Something that is not expected to bind there is coming and sitting there. Now, what we do is we design small molecules which, before this harmful binding can take place, can go and sit there. And if that can happen, then this harmful binding may be arrested, may not happen. And that is how most of the drugs that we take, the medicines that we take, that is how it acts. These small molecules go and bind to some target sites. And that is how so designing these small molecules essentially is an optimization problem. Because you see, there are electrostatic interactions going on. There are short distance van der Waals forces which are in action over there. So it's essentially an optimization of the energy. And that is what exactly we did. We took an algorithmic approach. We had an algorithm called genetic algorithms. So essentially what we were doing is, I'll not go into this genetic algorithms, but we were also looking at a multi-objective optimization. You see, multi-objective optimization is very interesting. You have, let's say, 2 objectives, both of which you want to maximize. But if you want to maximize this, this goes down. If you want to maximize this, this will go down. So how do you handle this such problems? This is called multi-objective optimization problems. It's like time and cost. You want to go from point X to point Y. You want to minimize the time. You want to minimize the cost. It is impossible to minimize both, right? You try to minimize the time, cost will go up. You want to minimize the cost, time will go up. So how do we solve such problems? That is what is multi-objective optimization. And we have our own algorithm for solving this problem. It's simulated annealing based method, which we call AMOSA. And we had this particular drug design problem. We had these 3 different objectives that we wanted to optimize. Okay, so energy components, something called Tanimoto coefficient and something called oral bioavailability measure. This is interesting actually, that suppose you design a small molecule, which will be your drug, but that small molecule is so heavy that it does not go inside the cell. Then it's of no use, right? It has to enter the cell before it can act. So that drug molecule has very nice properties, but it has become so large that it doesn't go inside the cell. So that's taken care of by such measures. It should be appropriate. And using that, we actually took the target of tuberculosis, Mycobacterium tuberculosis. This is REC-A is a protein of Mycobacterium tuberculosis. So this protein actually of the bacteria, for when the antibiotics, when a person takes antibiotics, then it damages the bacterial DNA. Okay, when we take antibiotics, the bacterial DNA gets damaged. REC-A is a protein of the bacteria which repairs the bacterial DNA. So it helps in the survival of the bacteria and in the spread of the disease. Now, if we can stop REC-A from acting, then maybe antibiotic will be effective, right? So that is what we did. We took REC-A as the target. And as you can see here, this was what, it looks very complicated, but we designed using our method, small molecules. And these small molecules were designed using our method. But these actually we found are known, already known reconstructed inhibitors. These are known to inhibit that particular REC-A protein. Okay. So there is nothing new in this. It's already known, it's there in the databases. But what we got in addition were certain other small molecules whose existence was not there in the known database. So this gives interesting information. Okay, the first slide here, reconstructing known inhibitors gives us confidence on the method. And the second slide here, the unknown molecules, this gives new information. Now it's for the biochemists to actually synthesize and see what is happening in the laboratory. So these actually are very interesting works, as you can see, and have very great real life applications. And that's how most of the pharmaceutical industry, they work. So I think I'll stop here. Some more predicted probable binders, but I'll stop here. We'll just acknowledging my institute, the different funding agencies that I have had the fortune to be associated with, and of course, all my students and collaborators across the world. I'll just open up for some questions. If you have, I'll be happy to answer, or any comments that you want to on whatever you've heard. Thank you very much. And thank you. If you look a little carefully here, you can see a face again of the founder of our institute, Mahalanobis's face. Thank you very much.
Thank you very much for the wonderful lecture, ma'am, wherein you clearly made us to understand the role and scenario of women in science and life as well, and about the artificial intelligence. Please be seated. And about the artificial intelligence and data-driven science, and of course about your scholarly research. Thank you so much. So now, ma'am, with your permission, we will have an interaction session. We will take a couple of questions from our colleagues. Yeah. No. Yeah. Yeah. Only, only 2 questions we can take. Yeah.
In drug designing, there is a term combinatorial chemistry. So how this is different from that, or what do you make these applications? Yeah.
You see this possibility, the combinatorial chemistry. I would not know that very well, but from from the word combinatorial, actually this is the number of possibilities are exponentially high, and there you would have been able to have confidence on your method if you could look at every solution, right? But that's not possible because there's a combinatorial explosion also of the size.
Suppose if I use AI and
Yes,
I
that is
think
where,
to bring it,
that is exactly
together
why
and
we
apply
used,
it.
that's right, that's exactly why we use genetic algorithms, as I said, something called or simulated annealing, because these have the property that where the search space is huge, huge in the sense that it is not possible to solve it optimally. There, you have to use these methods for optimization. Because you see, there are, it's a simple example. Suppose you have a 100 long string, just a 100-bit string. That means 100-bit strings means how many possible strings? There are 2 to the power 100 possible strings for 100 bits, 0, 1, 0, 1, 0, 1. Now, 2 to the power 100, if you want to analyze using a standard computer, it will take, it is not possible. It is not possible. That is a fact that if you just, suppose there's a computer, which is a very bad computer, let's say, which can process in 1 second 1,000 strings. It can process 1,000 strings in 1 second. From the time this earth was created till today, it would not have completed this of generating all the to the power 100 strings. That can be really worked out. So problems where of that magnitude, where finding the optimal string is not, or the optimal solution is not possible, that's where you have to use methods like simulated annealing, genetic algorithms, and of course there are enhanced versions where we also look at multi-objective optimization, etc. Yes.
Ma'am, you explained about the binding of molecules at tiny protein areas using this approach. So, have you also experienced something when there is a problem of dystrophy or dystrophin of muscles or proteins?
Dystrophy of muscles I've heard, but dystrophy of proteins, I don't know what it means. But do you mean that the protein structure has become distorted? Do you mean like
or it is completely deteriorating with age and time?
Could be, but see, protein is one thing. Muscle, these are tissues. Muscles are tissues, okay? And these are also cells, and inside those cells, there will be a large number of proteins which are doing various things. So these are two different things. If you're talking of proteins, it's one thing. Proteins are small molecules which are working inside the cells. And these tissues or the muscles that you say, they are two different things. So yes, the damage of the tissues of the muscle, there are proteins which would be playing active role in having those damages. And in order to do something about it, if there are medicines which are taken, it's essentially through these principles only that those medicines are identified. So what exactly you asked, I'm not very clear about it, but if the question is about destruction of the muscles, then yes, there will be proteins which are responsible for that destruction. And we may be able to do something about it, arrest the pace of destruction by taking medicines, but those medicines will attack certain proteins in the same way. The basic principle is the same.
Okay. So means like it will be involved in this genetic algorithm.
Genetic algorithm is a piece of software. It's a computer program. Okay, it has nothing to do with the real genetic systems.
Okay.
It is just a computer program whose task is to do optimization. It will optimize, it will give a nice optimal result for problems where finding the optimal solution within finite time is not possible. If it were possible, for example, see, if you want to sort a sequence of numbers, the worst case time complexity of sorting a sequence of n numbers is n square, which is fine. You should just do it. I mean, you should not use any such technique over there. But suppose you are trying to solve a problem where the complexity of the problem is such that the n, the size of the problem, goes into the exponent 2 to the power n. Then these problems blow up with time. I mean, with the size of n, it will blow up. Its size becomes so large, your search space becomes so huge that it is not possible to solve those problems. That is where you must use, or you can use, techniques like genetic algorithms. But genetic algorithms, remember, is just a piece of software, just a piece of code in the computer. So it has nothing to do with real systems.
Okay. Thank you, ma'am.
Last question from our.
Yeah, my question is inspired by this COVID-19. So it may be a layman's question, in fact.
I am also a layman anyway.
So when you have this virus, your algorithm, is it possible to identify those switches where you have these mutations which is going on?
Not
Is there a
exact-
possibility?
Yes, there is a possibility. Certainly, that is how
The locations can be predicted and can be.
Yeah, because that sequencing of all these viruses is happening. So we actually know the sequences. And from once you have enough sequences, then you can look at all those sequences and find out where where a particular mutation might have happened. It is possible. It is possible. And that is how it has been analyzed and established that there are certain, I'm now coming away from that particular virus, coronavirus, but let's say for breast cancer, cancer is very often a genetic disease. And there are certain mutations that may have happened, which is a trigger for the breast cancer. So breast cancer has very well-known mutations. And if, you might have heard about the story of Angelina Jolie,
Yeah.
who got her genome sequenced, understood that she had that mutation, which is established, well known, it's known very well. She had that mutation. She also had a family history, and therefore she took a preemptive step of getting a mastectomy done. So these are, it is possible to know where the mutations have happened, etc. And which mutations are associated with which diseases. That is also, it is possible to computationally know that.
Thank you.
Okay, one last question. Yeah. Yes, please.
So now this machine learning.
Brief, because you can ask in another.
She's a hard taskmaster.
Okay.
That is one challenge that is always happening. I mean, see, in computer science, the research can be in different ways. One is, of course, you find better and better algorithms. Like I said, if the time complexity of a particular algorithm, so generally that time complexity is a measure of how long the time will take. Not exactly, but is a measure. So if it is n square, if you can bring it down to n to the power 1.5, if you can sort of make it at least close to linear, then, and also people are looking at sublinear algorithms. So that means even less than the size of the problem, the complexity will be less than n to the power 1. So that is where algorithms are. That is one area of research that you develop better and better algorithms, which will require. But then often these these become approximation methods. So more error will be there. More error will be there in the result. But then if the problem is such that anyway, you have to live with errors. You cannot help it. So then you live with it. That's all.
Thank you so much. With lot of patience, you have clarified the queries. Yeah. Now, next program is felicitation to our women staff at NGRI. So may I request Professor Sanghamitra ma'am to felicitate our women staff who have received the awards and honors and extended their services in a great way. Yeah. First of all, I request Dr. Kusmita Arora to come on to the dais, and she has been elected as a fellow of the Telangana Academy of Sciences.
put it on your shoulder across your neck. What should I do? Thank you. Thank you.
Thank you. I request Dr. Tanvi, and she has received the Craig Baisley Award for Social Contribution by Society of Exploration Geophysics, USA, for the year 2021.
There, but there is something nice. Thank you.
Thank you. Next, Dr. Malika for Associate Fellow of Telangana of Academy of Sciences.
Wonderful. Congratulations.
And Mrs. Sindhuja for the Young Scientist Award by Telangana Academy of Sciences. And now it is a team award. This is by Dr. Manjula and Archana for getting for receiving IGU Best Poster Award. Maybe Dr. Manjula is in field, so Archana is going to receive.
Two of you. Yeah. Oh,
Yeah.
wonderful. Very good. Very good.
And it is my pleasure to invite Dr. Suchismita Pinjwal, our doctor in dispensary, by being selected as a member of Sports Commission Board by CSIR headquarters. I request Srimati N. Sai Kumari, Assistant Section Officer, General and Medical Sections, and she is retiring in the month of July 2022.
Long service.
Yeah, I request Srimati Maria Paul Chaudhary, Assistant Section Officer, Civil Section, and she's also retiring in the month of August.
Yeah.
Thank you. And I request now Srimati Reena Kumari, Lady Security Guard. Actually, she was very strict by making people to follow the COVID protocol and thereby making the institute very safe. A big round of applause to her. I think. Now, it is our great pleasure to felicitate our chief guest today. I request our director to felicitate the chief guest. Yeah, it is a Pochampalli shawl. Yeah, yeah. A Pochampalli shawl. It is a shawl, and it's a pure Pochampalli silk. Yeah. We have many peacocks in. Yeah, I was telling you. Yeah, yeah. In the evening, you can see many. Yeah.
Did you have a packet or something?
Yeah. Now I think yeah.
So now it's a time for vote of thanks for 1 minute. So my very special thanks to our special guest and for accepting the invitation to deliver a lecture. For me, her lecture was like a movie, thrill movie, because my concentration is very poor. But I could not even for a minute I could not. Her lecture was so continuation in continuity. First, okay. I thought she is taking back of her thing. So her lecture was her science, DIML, then everything was there in her lecture. It was such a beautiful lecture, madam. Thank you very much. And then thankful to everybody who are attending here and virtual also, because we could not invite everybody here. The last thanks to everybody who is coordinating the organizing this function. Thank you, everybody. Thanks a lot. Now, please, everybody, we need this rock garden for high tea. All who are not here, everybody who are there in virtual mode also, please come. Virtual mode है ना sir? हाँ, madam, everybody, whole institute, whole institute.